Okay, so it's just gone past the hour. So good afternoon, everyone, and thank you for joining this webinar. So my name is Phil Dent, and I'm the chair of the Marine Corrosion Forum. So firstly, I'd like to welcome today's presenter, who's Ross Hubble from COMSOL. So welcome, Ross, and thank you for doing the presentation. So I'd also like to welcome all Marine Corrosion Forum members and all ICOR members and any guests who have joined this presentation. So this webinar is the third in a series of 5 which have been organised for this week by the Marine Corrosion Forum and the Aberdeen branch of ICOR. So all the webinars are started at 12 noon UK time. So before we start, I have a few procedural matters to cover. So firstly, can you keep your microphones on mute, although Lewis will be muting these through the presentation. So if you have any questions, can you use the chat or message facility in the bottom left-hand corner of your screen, or at least it is on my screen. So if you just click on that, type in your question either during the presentation or at the end of the presentation, and then Ross will handle all the questions in order at the end of his presentation. So I'd now like to hand over to Mohammed Ijaz, who's the chair of the Aberdeen branch of ICOR, who'll do the introduction to ICOR and also the introduction to Ross and the presentation. So over to you, Ijaz.
Thank you very much, Phil. Much appreciated. And I would like to welcome everyone on behalf of ICOR Aberdeen branch, and thank you very much for joining us. You are the real factor to make these presentations or webinars successful. I would like to thank COMSOL team as well as Ross for presenting today. We have got very well attended ICOR MCF webinar over this 2020-21 technical session. This one being one of the highly anticipated webinar today, and hopefully we would have a quite good attendance. We usually announce our webinars on LinkedIn page as well as through the email that we sent out through our Google site. And if you haven't received any of the emails from us, please feel free to join us on the sites.google.com/ICORABZ. Just look for us, and there is a huge set of resources available in Google site as well as in icor.org/Aberdeen. We have got good 10 years worth of record and resources available free for you to use. We have been, during this COVID season, we have been actually recording most of our or all of our webinars, and we are putting them onto YouTube channel. Please feel free to go, and if you want to have a overview of any of the ones that you have missed, and that would be a good opportunity to join in there. I would like to thank all of our branch sponsors as well as sustaining and gold sponsors for ICOR, without whom it wouldn't be possible to organize these kind of things, and especially our ICOR Aberdeen committee, who are actually the real powerhouse for the webinar organizations. And thanks to all of you, of course, all the attendees who are making it successful. With that, I would like to introduce today's presenter, Ross Hubble. Ross works as an application engineer at COMSOL UK, and he previously worked as a process engineer for Jacobs Consultancy. He graduated from University of Cambridge in 2010 with a M.Eng in chemical engineering, and then he carried out his PhD investigating carbon oxides hydrogenation reactions. With that, I would like to request you all to welcome Dr. Ross Hubble, or put your virtual hands together. You can take over, Ross.
Okay, thanks for the introduction. So, hello, and in this presentation, we're going to be discussing sort of how we can simulate corrosion and corrosion protection systems using COMSOL multiphysics. So to begin with, I'm going to start by giving an introduction to what COMSOL multiphysics is, how and why we might use COMSOL, and then I'll briefly touch on some of the theory underpinning the simulations, and then highlight where the corrosion module and COMSOL can benefit in the simulation of corrosion processes. In the second half of this presentation, I'll give a brief demonstration of the software and the workflow and how you go about developing corrosion simulations, and how we can simulate the galvanic corrosion of a zinc nail. Finally, I'm going to highlight some of the available application examples describing the different types of corrosion processes we can simulate within COMSOL. And then, of course, if you have any questions about these, we can answer them at the end. So, COMSOL Multiphysics as a software offers a simulation platform for solving physical equations across a wide range of physics. COMSOL simulation itself is not exclusive to modeling corrosion processes, such as ion transport within your electrolyte or charge transport in the anodes and cathode materials. It can simulate electromagnetics, mechanical problems, heat transfer and fluid flow, as well as chemical and electrochemical reactions. The main advantage of the COMSOL multiphysics approach is that it allows the inclusion of many different equations and types of physics to be amalgamated together into a single model with a common user interface. And this approach is advantageous in electrochemical systems where the physics of charge transport and mass transport are going to be linked. So for a corrosion simulation, we might be interested in perhaps mechanical simulation as well, if we're investigating sort of stress corrosion processes. So this is where we can link our sort of structural physics together with our chemical physics. Another useful tool within COMSOL is what we call the application builder. The application builder allows you as a modeling expert to build your own graphical interfaces as an app on top of an embedded model. And these apps may be built for, say, a very specific purpose and may also be built for a specific audience. So through developing your own apps, you can then distribute your simulations to a larger community of designers, engineers, and scientists to benefit from the simulations which you've created within COMSOL. The apps allow for sort of control over the inputs which are given to your model, so you can limit the number of variables which can be changed, and that means you as the model designer has control over what the end user can change about your model. This allows for a simpler interface to be developed and specialized for your particular application. So even those without a simulation, much simulation experience can make use of the models you've developed. And with the COMSOL compiler, these apps can be compiled into executable .exe files, which can then make sharing your modeling work even easier. So how can we use COMSOL for a corrosion simulation? Well, the four key areas COMSOL can be used for is in developing understanding, predicting behavior, innovating change, and an optimization of designs. So for instance, if we're examining the rate of corrosion on an offshore structure, we could develop a physics-based model to simulate the current distributions across our structure. We can then use this to understand the impact of the design on our corrosion rates and predict where the corrosion is going to be most severe. Perhaps from this prediction, we can then determine how best to apply our protection system. So were we using sacrificial anodes, we could, for instance, examine how their position relative to the structure influences the level of protection they provide, and from this then infer perhaps an optimal configuration for protecting your structure. COMSOL as a software has a broad product suite, and physics applied in today's model are part of the corrosion module, an add-on product to the core package of COMSOL Multiphysics. The COMSOL Multiphysics core package provides the COMSOL interface, tools to represent geometry and mesh, and to appropriately sort of discretize your geometry for numerical simulation. In addition to these tools, the solvers required to run the models and a selection of physics are available. Through the addition of the corrosion module, the tools and interfaces necessary for modeling ion transport, charge transport, and electrochemical systems are added. The module also allows for the representation of corrosion over a range of length scales, whether this is simulating, say, the ion transport and concentration profiles within a crevice, or the current distribution across a wind turbine monopile. The corrosion module offers the ability to examine cases where electrode deformation is significant, or in cases where perhaps you have the dissolution of or deposition of species and how they affect your corrosion behavior. So, for example, if we are developing a calcareous layer on our electrode surface, and this may influence the rate of corrosion, we can calculate how this affects the corrosion behavior of your system over time. The other interfacing modules on the right here combine the strengths of COMSOL with various different CAD softwares and other tools which you might work with, which can be a real benefit to sort of streamline your workflow. The main sort of purpose of the corrosion module and its design is sort of made with space-dependent modeling of corrosion in mind. So it allows you to investigate the process of corrosion for a given geometry, or to optimize the design of a corrosion protection system. So on the right here, we have an example of a monopile being protected by an array of sacrificial anodes. We can model the rates of degradation and dissolution of the sacrificial anodes, and in turn then infer how well our corrosion protection system performs, whether this is the beginning of its lifetime or many years into its service. In the case of the example here, we can see the potential on the structure relative to a silver chloride reference electrode. So to begin with, let's take a brief look at some of the electrochemical theory underpinning these models. So when we simulate corrosion processes, what we model is basically a galvanic cell. The figure on the left here shows two metals in contact. Metal 1 acts as our anode, and metal 2 acts as our cathode. Sorry, the other way around. The direction of the current flows between the two metals and will depend on their position in the galvanic series. So the less noble metal with the lower, more negative electrode potential will act as the anode, and metal 2 here on the right is losing electrons to metal 1, which is our cathode, where the oxygen reduction reaction happens. This process can be represented across a range of length scales, so we could be interested in large-scale modeling of tens to hundreds of meters for cathodic protection systems, or very small if we're examining the complex chemistry and mass transport influences in a corrosion process, such as pitting or crevice corrosion. What we examine in our cell here is the transport of ions within the electrolyte for the transport of charge, and the transport of electrons in the electrode. On a micro scale, we might model this as diffusive transport of the ions to determine how the concentration influences the local conductivity. On a macro scale, we might assume a uniform conductivity and use Ohm's law to represent the passage of charge in the electrolyte. The corrosion module offers a number of different levels of model complexity, which allow you to customize your model to incorporate the necessary level of detail and accuracy for your system. It's also possible to examine systems where external currents are being applied, and this can be used to protect our cathode. For instance, in an oppressed current cathodic protection system, we'll again have our oxygen reduction on our cathode, and we may also have oxygen evolution or metal dissolution on our anode. And these electrochemical reactions will be forming the basis of our simulation of the corrosion process. If we look at a galvanic cell, we typically wish to represent the electrochemical reactions on a current density basis. This allows us to examine where the rate of corrosion is most significant and how fast the material is corroding. The representation of these rates can be achieved using electrochemical kinetic expressions to relate the overpotential, that is the driving force for the corrosion process, to the current density. COMSOL includes the Butler-Volmer equation, the linearized version of this, and the Tafel equations predefined to help facilitate easy definition of our electrochemical reactions. These standard electrochemical expressions can be parameterized to match your material kinetic behavior, and user-defined polarization curves can also be defined using the inbuilt interpolation functions. We can use these equations to determine the corrosion current, finding a balance between the cathodic and anodic currents to determine the corrosion current. This is demonstrated here on the right with our Evans diagrams and our polarization plots. If you're unsure of the data required to get started with the simulation, the material library within COMSOL contains a number of predefined materials with the electrochemical kinetics taken from scientific literature. This feature was added in our most recent version 5.6 and contains electrochemical data for steels and alloys of zinc, copper, aluminium, nickel, magnesium, and titanium. Many of these materials have these properties defined at different temperatures and different salinities, so it can provide a good starting point for your simulated material properties. In terms of the described physics and phenomena in the corrosion simulation, these are represented as conservation laws, so the conservation of current, charge, and material. These physics may be described by Ohm's law if we're examining the conduction of current within a solid electrode, or the Nernst-Planck equation if we're interested in the concentration profiles of the ions within our electrolyte. The electrokinetics can be concentration dependent, allowing the activation and concentration over potentials to be accounted for. The software also allows us to define multiple reactions on the surface. The influence of resistive films forming through the deposition of species, for example, calcareous layers, can also be accounted for. If the material is removed from the electrode due to corrosion, well, the amount of material being removed is significant. We can also account for the effects which the modification of the geometric deformation has on the physics. With space-dependent corrosion simulations, we can represent a variety of different corrosion processes. These include galvanic, atmospheric, straight current corrosion, pitting, crevice, and stress-induced corrosion. Provided the material and electrochemical data can be defined or represented using the predefined materials, a simulation of the process can be made. Corrosion protection can also be represented, for example, cathodic protection with impressed current cathodic protection, or the use of sacrificial anodes. The representation of film formation is also possible, and we can examine perhaps the anodic protection mechanism. So if we have a small passivating current to develop an oxide film in our system. So the way COMSOL represents physics is to use what we call physics interfaces. These interfaces contain all of the necessary domain and boundary conditions predefined for the representation of a certain physics. The corrosion module and the core COMSOL multiphysics package together include the functionality to represent species transport in free and porous media by diffusion, convection and migration using the transport of diluted species interface. We can also couple in laminar flow if we want to simulate fluid flow within our system. And these can be easily linked together either using multiphysics coupling or manually. The main concept with COMSOL and the COMSOL desktop is to make it easy as possible to link physics together and enable the development of high-fidelity models. The majority of corrosion simulations within COMSOL will use one of the current distribution interfaces we have here. These offer three levels of complexity for describing corrosion processes. The first interface, the primary current distribution interface, assumes charge transport is described by Ohm's law in both electrode and the electrolyte, with the potential between the electrode and electrolyte set by our equilibrium potential. The secondary current distribution interface allows for the incorporation of electrokinetics, and the tertiary current distribution interface further extends this capability by adding in the modeling of the ion transport in the system. This is particularly important in smaller scale corrosion simulations. So if we're looking at crevice corrosion, we might be interested in the pH and concentration changes within the crevice. In terms of how we can go about studying corrosion, we can look at this on either a transient basis, so we can simulate how an electrode will change in the form over its lifetime, or we can look at a stationary basis to see with that configuration sort of what the current and potential distribution over our structure will be. So now we're going to have a look at the corrosion module and its benefits and capabilities in a little bit more detail. So in terms of the main benefits we have with the corrosion module is that we can combine a lot of detail with our physics and our chemistry together within our single model. So we can account for the detailed physics and chemistry of, say, our crevice corrosion here, so we can look at the concentration profiles within our crevice. But we're not limited to just looking at small structures, so we can, again, look at perhaps our larger structures, so our oil platform here. And the main advantage of COMSOL is our multi-physics approach, so we can bring in extra factors such as heat transfer and transport of species to examine how, say, oxygen transport within our electrolyte domain influences our corrosion rate. And we do have a number of simplifications available for helping you model large-scale structures as well. So, for instance, if you had several oil platform legs here. So the way COMSOL models corrosion processes, well, the main numerical model used is the finite element method. And for certain types of systems, we also offer the boundary element method, as this can be a better way of modeling sort of large-scale systems. So the main reason this is useful for modeling large structures is it is a slightly more memory efficient method of representing very large domains. So if you had, say, your oil rig within the C domain, there are a few different approaches to modeling this, but the boundary element method can be quite useful in representing a very large, expansive electrolyte, essentially. We do have a few additional features as well, which can help in the modeling of corrosion simulation, because most corrosion happens in a very large domain. It's often going to need some simplification to reduce the memory requirements. So we do have edge-based electrodes to help represent slender structures, and in representing the structure as an edge rather than sort of explicitly meshing it as we would here. This then reduces the memory requirements to make sure simulation more efficient and quicker to solve. We can account for the deposition of or the dissolution of species on the surface, and we can either account for that just by sort of summing up the amount which has been deposited, or we can actually see how the electrode surface deforms using a moving mesh approach. For large pipeline structures, it's often more convenient to use a 1D pipe formulation, which we've developed to look at the corrosion within the system, because they can be sort of very long and linear structures, and if you're modeling that strictly with the finite element method, that can use quite a lot of memory. So we do have a more memory efficient method for representing that. And in terms of additional features, we can also represent sort of experimental techniques, so your standard electrochemical impedance spectroscopy or cyclic voltammetry. These can also be represented using the functionality within the corrosion module. Okay, so that is our introduction to COMSOL and simulating corrosion within COMSOL. So now I'm going to give you a demonstration of how we might go about using the software to simulate a corrosion problem. So in this simulation, what we're going to be looking at is a galvanized nail. So we're going to have the nail within a wooden domain which is wet, so that's going to be acting as our electrolyte. We can then use this to determine the corrosion rate of our nail, and then we can also add in the transport of oxygen to examine how that influences our corrosion rate. So to do this, what I'm going to do is I'm going to open up COMSOL, and when we open COMSOL, what we're presented with always is our new screen, and what we recommend doing is selecting the model wizard here. So the model wizard really accelerates getting started with our model and just asks us a few questions about what we're simulating, and then we'll sort of walk us through the initial setup. So we select the model wizard here, and then in this case we're going to select a 2D axisymmetric component to represent sort of the domain around our nail. So we offer sort of many space dimensions, and we do recommend going for the lowest space dimension possible, because that again reduces the memory requirements for your simulation, will lead to a quicker and more efficient simulation. So for the 2D axisymmetric here, we'll just select this, and now we're presented with the physics. So we're looking at an electrochemical problem, so we're in the electrochemistry branch. And then we're looking at the secondary current distribution. So what we want to do is want to model the potential profile within our electrolyte, look at the current densities to examine sort of how fast our corrosion process is occurring, and we're going to use sort of the electrochemical kinetic equations, such as the Tafel equations, to represent this behavior. So one of the nice things about the pane here is that if you're unsure about which physics interface you want to use, there is a nice sort of description on the right here. You might notice the corrosion one here as well. So what the corrosion one here does is it adds in the ability to include deforming geometry as well. So in this case, we're not going to add in the deformed geometry. We're just going to look at the current distribution on our nail to keep the model relatively simple. So clicking study, we can now select our study type. So these are the study types which are compatible with our selected physics interface. So we can have a stationary, a time-dependent, frequency domain studies, and then we have some special studies for experimental techniques such as cyclic voltammetry. So we'll start off by going stationary. Now clicking done, this will bring us into the COMSOL desktop, and the COMSOL desktop here consists of sort of 4 main windows, and this is our main working environment. So what we have on the left here is what we call the model builder, and this gives us sort of an overview of our model structure. So we basically recommend starting from the top and then working down to the bottom to give you a nice logical workflow for your system. So we start first by defining our parameters, and then if we have any additional definitions such as functions or variables, we can define them here. We then add in our geometry, assign a material to our geometry, set up our physics, discretize our geometry using the mesh node, and then run our study to get our results. And you might notice as I was clicking down the model builder here that the settings pane here changes based on what we're clicking on in the model builder. So this gives us a context sensitive menu where we can make our inputs. So for instance, the electrolyte node here, we can specify our electrolyte conductivity. We can either take that from the material or we can use it to define it. On the right here we have the graphics window. So this gives us a visual representation of our geometry and also can help in assigning our boundary conditions. So you don't have to remember sort of a numerical value for a boundary. All you need to do is click on it within our graphics window. And then finally we have the messages window at the base here, which can give you a little bit of extra information about what's going on in your simulation. And depending on how you like to work, you can either use the right-click menu on the model builder to select basically the options for each of the nodes, or you can use the ribbon tab up here to select your geometry options. So I'll start by building our model. So I'm going to start by defining some parameters. And to save a little bit of time, what I'm going to do is load these parameters in from a file, just so you're not watching me type all of these out. So we have a geometric parameter for our nail length, an electrolyte conductivity defined in Siemens per meter, and then we have our equilibrium potentials, so our zinc, our oxygen, and our iron. So in our simulation, we're going to have a nail which has sort of zinc on the outside, and then at the tip we're going to have some exposed iron. So we're going to have our corrosion occurring between those two surfaces. We also have our electrochemical kinetics here. So we have our exchange current density for our oxygen reaction, our exchange current density for our zinc oxidation, and the same for our iron oxidation. Moving on down, we're going to define our geometry. So I'm going to save a little bit of time here by inserting the sequence. So I'm going to bring in our galvanized nail geometry. It's relatively simple, so it's made from a square, followed by a polygon to define our nail. And then we're going to use a difference operation to cut the nail away from our wet wood domain. So why we're doing this is because the nail is going to have a lot higher conductivity than our wood domain. So essentially we can assume that the potential within the nail domain is uniform. We don't then need to actually simulate the electrode itself, because meshing this would be sort of extra mesh, which isn't necessary. So if we then form a union, this finalizes our geometry. So moving on down to our secondary current distribution interface, what we're going to do is first define our electrolyte conductivity. So this will be our parameter sigma. So I think that was 0.005 Siemens per meter. We can then define our electrode surfaces. So what I will do is right-click our secondary current distribution, select an electrode surface, and then click on our zinc electrode surfaces here. So if we just zoom in, I can then click on this one up here. So we're going to say that these are our zinc exposed surfaces in contact with the wood. And to make it a little bit easier as well, we can just create a selection as well. So this allows us to name a selection of boundaries and give it a nice recognizable name rather than just 4, 5, and 6. So on this surface, we're going to have our zinc oxidation reaction. So our equilibrium potential for this is going to be EEQ_Zn. And then we're going to define this using the anodic Tafel equation. So our exchange current density, again from our parameters, is I0Zn, and our Tafel slip is A_. So that defines our zinc reaction. We now want to define our oxygen reaction on this surface as well. So we can have multiple reactions on the same electrode surface. So we can just right-click and add a new electrode reaction this way. And now again we're selecting on these boundaries for our electrode for our oxygen reaction. So we'll set our equilibrium potential as EQ02, and then we'll set our Tafel equation being our cathodic Tafel equation. So our exchange current density will be our I naught O2 on zinc, which is another one of our parameters, and then our Tafel slope will be A O2 zinc. So then that defines our electrochemical kinetics for that reaction. So that defines one of our electrode surfaces. We now have another electrode surface here, which is where the iron is in contact with our wood. So what we're going to do to save a little bit of time is just duplicate this one. And then we'll deselect the zinc boundaries and just clicking in the graphics window, select our iron boundary. And to make that a little bit simpler, I'll just give that a name of iron as well. So expanding this, because we're no longer defining a zinc boundary, we just need to change the equilibrium potential to be iron, and the same for our Tafel equations. And then moving on to our oxygen reaction, we just need to then change our zincs to be iron. And then that defines the electrochemistry for our system. So we have the two electrode surfaces defined. One thing I will do is I will set our initial values for our electrolyte potential to be minus EEQ underscore zinc. So what this does is it just puts the initial potential, which COMSOL uses as a guess, closer to the actual value rather than just being 0. So it's just going to be based on our zinc reaction here. So moving on to our mesh, what we can do is we can build a mesh. So there are a number of different predefined sizes. We can also customize our mesh as well, so we're not limited to the predefined sizes. So if we select edit physics as you sequence here, we can then change everything about our mesh. So we're using a free triangular mesh, and perhaps we want a little bit more detail around our where our electrode surfaces meet here, so we can see if there are any sort of subtleties in our current density. So to do this, what we can do is we can define a size node, select our boundaries. If we select those boundaries there, we can then I also select these ones. Let's say set these to extremely fine, and then that makes our mesh around these boundaries a bit finer. And perhaps if we're very interested in where the two electrode surfaces meet, what we can do is we could even refine around a point. So we can select that point there and say, let's put the maximum element size at this point to be 0.1 millimeters. So then if we refine that even more, we can then see there's more mesh in that region. So running this study now should give us a potential profile within our electrolyte in the wood, and allow us to see that the current density distribution for our nail. So we can see the electrolyte potential, we can see the current the streamlines for our current density, and we can even plot what the oxygen reaction current density will be. So creating a 1D plot group allows us to make a 1D plot, and then I'll select a line graph, and now we can look at this boundary here where our iron is exposed, and then I'll just use the replace expression button to find the variable which we're looking for. So we're looking for an electrokinetic variable, and we're looking for the local current density for reaction 2. So that's our oxygen reaction there. So plotting that, we can now see how that varies across the length of the nail there, or that surface which is exposed. So that's a relatively simple representation of the system. So what we might actually have is a oxygen concentration dependency for our system here. So currently we don't have any mass transport for our oxygen included. We're just having a Tafel expression to represent the behavior. So what we can do is we can actually add in another physics to represent the diffusion of oxygen within our wood. So if we select add physics here, and then I go chemical species transport, we can then select the transport of diluted species. So opening this up, we don't have any convection within our wood, so we can deselect that. We can then select our transport properties, so we're going to say that our diffusion coefficient for oxygen in our wood is DO2, so that's just one of our parameters. Wherever you can sort of write a number, you can also put a parameter or a variable. So if this was a concentration dependent value as well, you can define a function and then specify that here, and COMSOL will use that variable as your diffusion coefficient. So what we want to do is we're going to say that our oxygen is coming from the top surface here. So we'll say that we have a concentration boundary condition on the top here where we're defining our oxygen concentration. So that will be CO2 reference. And we'll say that initially the concentration for our oxygen within the wood is also CO2 reference. And what this interface solves for is the diffusion equation. So it's solving for Fick's law essentially within the wood here. So that basically defines sort of our initial condition for our oxygen and where the oxygen is coming from. So now we just need to define how it's being consumed at our electrode surface. So to do that, what we can do is select our surface reaction electrode surface coupling here. And first I'll define it for our zinc boundary. So because we use the selection, we can just select zinc there. And then our reaction coefficients will be defined on our electrode reaction. This one, so it's this electrode reaction here. If we changed its name, it will also reflect that. So we can say oxygen reaction. And now we can see that reflected here. Well, once it updates. So with this, we can select the number of participating electrons to be 4 because we have O2, and then our stoichiometric coefficient being -1. So that defines our zinc behavior. We can now also define the same behavior for our iron section of the nail. So we select the selection to be iron. We can then use the same participating electrons and stoichiometric coefficients. We just need to link it to our iron reaction, which is this one. So we can see the tags there, ES2, ER2. This is then our iron reaction. So that then sets up the transport of our oxygen within the system and links it to our electrochemical reactions. Now, what we want to do is define how our electrochemical reactions change with concentration. So with this oxygen reaction on our zinc, what we can do is define our exchange current density as being concentration dependent. So we can have CO2 underscore. Right, so we're saying it basically scales linearly with oxygen versus our oxygen reference concentration. And the same one for this. So this is our oxygen reaction on iron. And what we can do here is we can again say our exchange current density is scaling linearly with our exchange current density is scaling linearly with our oxygen concentration versus the reference. So to be able to compare these, we'll first create a copy of our our solution we solved without the mass transport, and then we'll solve it with mass transport. So first, to start the solver in a reasonable place, we'll first solve for the potential field, and then we'll have a second stationary step to solve for both of them together. So if we start from the original answer, which we had, and then modify it to include mass transport, it'll be quicker to converge because we're starting from something which is quite close to the solution already. So if we now click compute, this then gives us a similar looking plot for our potential field. We can also see the concentration profile as well. So if we just make a new plot, surface plot, and then our concentration variable is C, we can then see that we have a little bit of oxygen depletion around the iron surface there. And then if we want to see how the current density changes between the two systems, we have this one. We'll set this as being our original current density, and then we can have another current density for our oxygen reaction being represented for our current solution where we're including the mass transport. So now we can see that with the oxygen transport, the current density is lowered slightly. Okay, so that basically shows how we can set up a simulation within COMSOL to represent a corrosion process and couple mass transport within it. So other processes which we might be interested in representing would be something like cathodic protection of an oil platform. So generally we're going to be interested if we're looking at offshore corrosion in something like our oil platforms. And the way which we can do this is very similar to how we set up our galvanized nail example. So it's using the same physics interfaces and the same definitions. And I have I have an example here which is open. So this one is just using the primary current distribution instead of the secondary. So it's just slightly simpler in that it's assuming that the electrokinetics of the system are fast. We have an electrode surface defined as we did in the previous example, and then we just set a current density on our structure there. So we set that as being our oxygen current density. And then from this we can examine how the steel potential changes based on its position and sort of based on the arrangement of the anodes as well, if you wanted to change that arrangement. And this model here is using the finite element method, but it's also using one of the nice features within the corrosion module to help you simulate larger systems. So this outer cylinder here is represented using an infinite element domain. So what this does is essentially stretches the elements in this region. So instead of representing a cylinder which is 100 meters across, this is actually scaling by a factor of 1,000. So what this cylinder then represents is essentially an infinite C domain around the oil platform here. So then this can help you get more accurate results for your potential. So you're not applying erroneously an insulation condition at the edge of a very small simulated domain. So I also mentioned the boundary element method. So this is demonstrated here in our multiple oil platform example. So here we're representing the structure. So in the previous oil platform, what we had is actual cylinders and beams representing our oil platform and our anodes, but we can simplify this down to be edges, and then with these edge electrodes you can then just define the radius of the edges, and this saves a lot in mesh because you can see that it doesn't have a domain around these edges anymore. So in using the current distribution boundary element method, this can slightly more efficiently work out the potentials within the structure for very large systems. Okay, so we do have a number of tutorials within our application library as well. So I'll just run through a few of these to highlight the different types of corrosion which we can represent. So just hopping back to the COMSOL briefly, I'll show you that where the application libraries are. So these are file application libraries, and then we can see the different examples here. So the one which we just went through was the galvanized nail, and if you wanted to repeat the example as well, it all has PDF instructions detailing the theory, and then modeling instructions on exactly how to set up the model as well. And each of the examples which we'll show in the slides have their own instruction manual as well. So if we just move through, just to quickly show the different types of models which we can represent, and then we'll have time for some questions as well. So we have an example for crevice corrosion, so we can see how the pH and the concentration of iron within the crevice changes. We can also look at how the crevice deforms if we're actually having material being removed from the crevice. We have atmospheric corrosion, so if there is a thin moisture film, we can see how that influences the corrosion between a bolt and two metal parts or other structures. We can also simulate internal corrosion in pipes. So this is using the special pipe formulation where the pipes are represented as edges. And because they can be quite complex in terms of their form like this, using the 1D tangential formulation significantly decreases the memory requirements and makes it a lot quicker to compute than it would be if we represented it fully as a 3D system. We can also simulate stray currents with this example, and we can look at stress-induced corrosion as well. So this couples the corrosion interface with our solid mechanics interface to represent the stresses within the system, and then you can define your corrosion potentials and exchange current densities based on the local stress then. So those are just a few highlights of the applications within our application library. So we have a list here. So we have CO2 corrosion as well, which if you're interested in pipeline corrosion, this can be quite an interesting model as well. So these are all within the application library. Okay, so I hope you've enjoyed this introduction to the corrosion module and how we can go about modeling a corrosion system within COMSOL. And if you do have any questions, I'm all ready to answer.
Thank you very much, Russ, for your excellent presentation and very interesting model for corrosion modeling, COMSOL model. We have few questions in the chat box, and we are going through this for next 15-20 minutes. Thanks for everyone who has asked questions. If you have questions, please feel free to add while we are going through this. So the first one I think is partly answered with your final slide, is from Urvish Wala, asking about possibility of doing corrosion modeling for different corrosion mechanisms like CO2 corrosion, amine corrosion, and the effect of different process fluids like H2S, CO2, amine with different concentrations.
Yep. So essentially, all you need with the to define your corrosion is going to be your your exchange current density and your equilibrium potential. So with our material library as well for the corrosion, there are a number of different materials already defined. So we have sort of different aluminiums in different materials. So these are taken from the literature, so they can be a good starting point for your simulation. So we have iron alloys as well, copper. And if in terms of how to approach different types of corrosion, the application library does have a number of different types already defined. So these models, while perhaps they're not going to match exactly your application, they can be a good starting point in seeing how the model can be set up and defined, particularly for the CO2 corrosion model here for pipeline corrosion as well.
Yeah.
Yep.
Okay, thank you very much. Just a question here from myself. Is your CO2 corrosion based on specific model like Dewar milliamps or any other known CO2 corrosion models?
So this one's just a 1D model of the turbulent boundary layer on the pipe. So what it's doing is it's simulating the equilibrium reactions for our water, for the dissociation of our CO2 and carbonate species, and then at the surface here we have our ion reactions as well. So I think this is our ion dissolution reaction, and then at the boundary of our turbulent boundary layer we have our concentration constraints. So these will be our bulk concentrations of our CO2, our hydrogen ions, and then our ion species. If we look within our application library at the PDF document as well, many of them do have references of where they're taking sort of the models from. So it'll be based on these papers here.
Okay, yeah, got it.
Yeah.
So we have the reference here as well.
Yep.
Okay, and these are kind of purely mechanistic models, or do you have any real field data used for enhancing the model?
So, I mean, if we're using the materials from the library, from the corrosion library, these are taken from scientific papers, all of the data from here. So I guess that would be as close to sort of your real field data as we have. Otherwise, the definitions of the reactions are sort of mainly used to find as to which processes are going on. So the main definition will be in our electrode surface, where we're defining our equilibrium potentials and our exchange current densities.
Yep, thank you. The next question is again from Orvesh Vala. He's asking if this software is used or can be used for the designing equipment, selecting the piping material, for example, or is it just purely for corrosion rate evaluation software?
So I mean, if you create your simulation for your corrosion, examining your corrosion rate, what you can do is you can, if you want to test how different materials behave, if you define your material within a material node, so say we had a few here, what we can do is we can define a material switch and then put these materials within the switch. If I just drag them in. And then what we can do with this is we can then run a material sweep study. So then that will repeat our study for each of the materials which we've defined. And then we can use that as a means to compare how each of the materials performs in our corrosion simulation. So if we had, say, an amount which we're losing each year that we wanted to sort of stay below, then we can use sort of the right values to examine the amount which we're losing for each of the materials, and then sort of work from there in our design.
Okay, yeah, thank you. The next question again from Orvesh, asking about the possibility of studying the coating effects for the underground piping.
Yep. So if you have a coated material, we can either have a deposited species on our material, which we can define within this node, and then we can associate a film resistance with that based on sort of the thickness and conductivity of our defined system. So if we have that, we can sort of define our thickness and conductivity. Alternatively, we can have sort of different electrode surfaces, as we did with the nail, each of them having different properties depending on where you're defining your coating.
Mm-hmm. Yep. Thank you. The next question from Falah Al-Kabi is asking, can COMSOL be used to describe the corrosion in reactor under supercritical water conditions?
I think that's a bit more of a difficult question. So it would really depend on how complex you wanted to define the corrosion. So what we can do with the current distribution interface is, if you're not sort of concerned about mass transport, then you can simulate the potential field and the electrochemical kinetics. I think the main challenge with your supercritical water reactor would just be having accurate parameters for your equilibrium potential and your exchange current density.
Okay. The next question is from Marco Tironi, who's asking, I would like to ask how to simulate interface phenomena in COMSOL. For example, a fixed offshore platform whose catalytic protection system interfaces with a buried pipeline which is near to the ICCP anodic system installed on the seabed. Yeah.
So we do have an example for sort of stray currents here. So we do have a buried pipeline crossing an impressed current cathodic protection system, and then we can see the corrosion in a non-protected pipeline. In this example, it's using the boundary element method, so it is quite plain to look at. It's just some two lines to represent our pipe, but we can do it with this model.
Okay. Yep. Thank you. The next question is from Orvish Wala again. Can we use this software for ICCP system in rebar concrete construction?
Yeah, I don't see why that would be any more different from the other ICCP simulations. So we do actually have cathodic protection in concrete as an example here. So this one has our rebar simulated here, and then we're modeling the diffusion of the oxygen from the surface to the bar there, and to just apply the current to the surface, we can set the potential applied to the electrode surface just through the definitions within these nodes here.
Okay. Yep. Thank you. And the next one is actually a comment by Adisiji and Jorin, is mentioning that the application library for the tutorial is a very useful addition. Chris Gugan next is asking, during your galvanized nail example, you only seem to obtain a very small change in oxygen reduction current density when you moved from tuffle control to diffusion control in wood. This conflicts with diffusion control in other environments, for example, seawater. Have I got this wrong?
So, I mean, you are correct in saying that there was a very little change, but that's only because the oxygen concentration in our system didn't change very much. So it only went from 0.2 to 0.19. So, I mean, the reasons for this could be that perhaps the diffusion coefficient we've used is relatively high, but also because it's also on quite a small length scale. So it's only a few centimeters there. And if the rate of corrosion as well is not very high for our nail, then the rate of mass transport might not become limiting. So through combining the two different physics, we could see whether there is a significant influence of mass transport or not. So in this case, it's not very significant, but if we do have significant mass transport in our system, we can predict it as well by coupling the interfaces in this way.
Yeah. Okay. Thank you. Next one is from Bayu. Thanks for the presentation. Please advise if we can use COMSOL for sour corrosion prediction for wet gas pipeline. He wants to understand also the impact of chloride.
I'm not entirely sure on that one because but basically, if you can define the electrochemical reactions which are occurring, as well as the chemical reactions, so as we had with the CO2 corrosion, we have the equilibrium reactions defined, and we have the reactions, electrochemical reactions which are going on at the surface defined as well. So it doesn't really matter which species you have involved, as long as you can define sort of the rate of conversion between the different species and the electrochemical kinetic parameters, so your equilibrium potential and your exchange current densities.
So mainly asking about sour corrosion. Is possible that to add H2S impact in the CO2 corrosion?
I think that's probably something we'd have to look into in a bit more detail. After.
So probably at the moment it's only sweet corrosion, only with CO2, not having the impact of sour corrosion and H2S.
Possibly, yeah.
Yeah. Okay. So the next question is from Urveshwala. What material range this corrosion software addresses, and does it include non-metal material?
So the materials included in the library are mostly metals in this case.
Okay.
Yeah. So yeah. I mean they're all metals and alloys, I think.
Okay, thanks. Armin Shoab is asking what model formats of the asset can be used with COMSOL, CAD, SolidWorks, etc., and which is the preferred type?
So in terms of the different CAD geometries which can be imported, it's actually quite a large number. So we can work with sort of AutoCAD, SolidWorks. There's a sort of exhaustive list on our website as well. So I think if we go 3D and then if you go import, we can also import mesh files as well. So the 3D CAD files would be the way to do it. So just by clicking browse and then importing your file, you should be able to get the CAD file in, but there are a large number. It supports basically all of the software which we had listed here for the live links. So we can do SolidWorks, Inventor, AutoCAD, Revit, PTC, and Solid Edge.
Yeah. Okay, clear. Thank you. So the next question is from Michael, asking if COMSOL can handle MIC, microbial induced corrosion.
So we don't have anything which explicitly would represent sort of microbial corrosion. I mean, if you can, again, if you're able to define the reactions which are happening at your surfaces, and you have an equation to represent sort of how the microbes grow and interact with your surface, then we can sort of add that in. So it's fully flexible. If you do have just a mathematics equation which you want to add in to represent your behavior, you can add in your own PDEs and ODEs to couple with your corrosion problem as well if you have a particular thing you want to implement.
Yeah, for MIC, I think it's very unlikely that you could find anything like this. It should be mainly on the real field data, different types of bacteria. So the next question is from Tommy Wang. Same query about ICCP in concrete that you already have answered. And the next one is from Anna. Some papers don't give directly the value of current density. Rather, they provide an exponential relations between current density and electrode potential. Could we add equations in the current density that consider a variable potential?
So, I mean, if you do have, say, a polarization plot, what you can do is you can just create an interpolation function, and then you can provide, say, your current density versus your potential in there, and then you can use that as an input for, say, one of your, current. So instead of using a kinetic expression, we can just go user defined, and then you can define your current density this way.
Okay, yeah. Thank you. And I think that's all the questions in the chat box right now. I don't see anything. Oh, yeah, just one more appeared right now from Adesiji Anjorin. A comment for other corrosive species like H2S, ethanol, etc. The dissociation and transport would have to be modeled and layered over the CO2 corrosion model in order to see their influence. Basically, as long as the chemodynamics, chemistry, and reaction dynamics are understood, COMSOL can be used to model different electrochemical phenomena. It's a tool and its efficiency lies in the hands of the user, unless I'm wrong.
I mean, I'd agree with that, yeah.
Yeah, that's what I understood as well, yeah. Okay, good. Thank you very much for all the questions, and thank you, Ross, for answering all of these in detail. And with that, I'm handing this over back to Luis for final notes about maybe tomorrow presentation.
Yep, thank you, Human. Thank you to everyone who attended today, and also thanks to Ross for giving us quite an in-depth presentation there. I certainly enjoyed it, and judging by the questions, a lot of other people did as well. Just to remind everybody that I'll be issuing the feedback flyers within the next hour or so. Please fill these in to qualify for your CPD certificate, and we'll aim to get these out to you in the next few weeks. Just remind everyone, if you haven't already signed up for tomorrow, we'll be back at the same place and the same time with a presentation from Spear Hunter tomorrow on the developments of remote magnetic monitoring of carbon steel pipelines to locate and measure abnormal stresses. So until then, everyone take care, and thanks again for joining.
Okay, thanks, Lewis. Bye, everyone.
Thank you.
Thank you.